question.
So you mentioned 7 nanometer, 5 nanometer, and you pointed out that we're getting less and less benefit for these extremely difficult transistors to produce. So you didn't go very much into what is the effect of this slowing down of Moore's law to the evolution of computer architecture, especially RISC-V. I would add to this that the really big problem in technology.
I would add to this that the really big problem is not even just the transistors aren't getting that much faster, but the metal is getting terrible. It's extremely slow, and it's getting worse all the time, such that interconnect and the influence of interconnect is a major problem. And I'm wondering what your thoughts are. What's the influence of these two technologically related issues to the architectures you described?
Yeah, so basically, you can think of, the Moore's law and Dennard scaling provided technology, but architects had to figure out how to turn that into performance or energy. But that was available to us. But it was still the architects had to do that, right? They're designing the caches and stuff like that. It was easier to do. That era is over, right? But so what's going to happen now is architects are going to have to do that they're going to have to deliver improved energy and performance without better transistors or with worse metal, right? And so I don't even quite understand if the transistors are the same cost, what's the benefit of going to a new technology? If you're power constrained, you could have more transistors that maybe you just leave them off when you're not using them, but it's harder to see the benefits. But from an architecture perspective, what we're going to do is, so what I tried to show there, like with the TPU, there was factors of 20 or 40, giant factors, orders of magnitude factors by specializing. We're only going to do this right. So it's kind of like, well, the other way, if we didn't specialize, the other thing we would have to do, if we were software people, we wanted to go faster, we're going to have to make our software more faster, right? So I show you the Python, the potential split up for Python. So either we're going to get speed ups as an industry by making software much more efficient than we've been in the past, or we're going to do these special purpose architecture things. But so the action, so the fact that if it comes to a dead halt, there's really no future process technology, there's still going to be a lot of innovation available for people who design chips. It'll just be frozen. We're not used to that, but that's the way I think it's going to be.
I think you said that the hardware is getting to be the bottleneck, and that
well, I wouldn't say the hardware is it's just we've lived for 50 years we've had this tremendous benefit of much better transistors every couple of years. What a huge, more of them, and they're faster and lower power. What a great time. That era is over. And so we're going to have to innovate some other way. And now the flip side of this, at the Achilles heel in my arguments about the golden age is CAD software, which is extraordinarily expensive. If the process technologies grind to a halt, which they're doing, or another way to say that is 28 nanometer isn't going to go away. That's going to be an attractive technology. It'll be more plausible for open source CAD software to be developed, which would bring the price down the CAD software to be affordable for other people, which is a practical obstacle for many people designing hardware is buying the ECAD software. The slowing down in technology may mean that we can, like it used to be in the 1980s, where universities would build CAD software that we could design chips with. So that would be kind of another upside. So for me, like I said, if you're an architect and said, hey, your old architecture is not going to work anymore, we need more architects to make things better, that's thumbs up. Maybe bad for companies.